Good morning, everyone. Welcome to my lab. Today I will be using this odd-looking contraption to demonstrate that carbon dioxide emits infrared radiation. This demonstration does not prove that climate change is happening. It does not disprove it. My intention is to merely demonstrate in a hands-on way one of the important principles involved in heat exchange between the Earth, the atmosphere, and outer space. The primary apparatus for this is a cone. It's in the neighborhood of 2.5 feet tall. It's made of a series of duct reducers, and the material is galvanized steel. The cone will rest on this base. It's made of the same material, and a bowl of ice will go inside it. The bottom of the cone is covered with a plastic sheet. It's not high-tech material. It's actually made from a plastic bag that I got at a grocery store. What this sheet does is it contains the gas inside the cylinder, but it also allows infrared radiation to pass through it. There are several temperature probes attached to the cone to monitor its temperature. They are glued to the outside of the cone. You can see that if I touch this, the temperature starts to go up immediately. So they're very sensitive. And there are two other temperature probes, one in the middle, one near the very bottom of the cone. There's a hole here. This allows the gases that I fill the cone with to drain out. The glass probe goes to the level of this temperature sensor when it's inside. And so this hole allows the heavier gases to drain away from the area where the glass probe is. That's important because it ensures that the glass probe is always surrounded by air and not the oxygen or the carbon dioxide. Oxygen and carbon dioxide have different rates of heat transfer due to convection. And so if you allow the glass probe to be surrounded by different gases and different runs, the difference in the rate of convection might affect the results. So this is one of the controls in the experiment. So here's the assembly that goes into the top of the cone. The main piece is this glass lens, and there is a temperature sensor glued to it, and it's covered with a piece of tape, which is basically paper. I chose glass because it has a very high emissivity. It radiates almost 95% of the maximum possible at any given temperature, whereas the surface of the cone radiates less than 1/10 as much. It's mounted on a wood dowel that conducts very little heat in from the outside. This piece of bubble wrap serves as just a platform for this to be mounted on. It has an aluminized surface, so it's a metal surface like the inside of the cone, which is important. And this goes into the top of the cone. We'll see what it does in a minute. So the first thing we need to do is put some ice in a canvas bag. Now that I have my crushed ice, I will make the ice and salt mixture. First I zero the scale, and then add ice. get it so it's 9 ounces. Then zero it again. So now I'm adding salt until I have 3 ounces. And with 9 ounces of ice and 3 ounces of salt, that'll make a 3-to-1 weight ratio, and that'll get it nice and cold. After adding the salt, we give it a nice stir and zero it again and add more ice. We'll repeat this until we have like 2.5 pounds of ice and salt together. I just put a thermometer probe in the ice mixture. It's reading -16°C and eventually will read -18 or 20. Much colder than regular ice, and therefore it will make a much more effective demonstration. So here's the bowl of the salt ice mixture. It goes into an insulated bowl I made for it. And then this duct reducer goes around it, fits nice and snug. And this duct reducer is just meant to provide spacing between the ice and the bottom of the cone, which rests here. So this thermally isolates the cone from the ice so that there's very, very little conduction of heat from the cone down to the ice. The primary type of heat transfer is by radiation, not conduction or convection. Before we do any experiments with the probe inside the cone and using different gases to see what their effect is, let's do something simpler where we're just going to expose the glass probe to ice, and its temperature is 21.1 degrees. So now we'll move it directly over the ice and see what happens. So you can see the temperature started at 21.1 degrees and now it's falling steadily. And after 5 minutes or so, we see the temperature has dropped pretty significantly to 17.6 degrees. It started at around 21. Here's how we understand what's happening with the probe in the ice. Before the probe is away from the ice and it's just exposed to all the surfaces in the room, all surfaces always are radiating infrared, even very cold objects. You could have a brick out in the snow and it would be radiating. Not very much, but it'll be radiating. Things radiate when they are obviously warm, and they also radiate when they're just simply at room temperature. You don't notice them, but they are. And so the glass probe is radiating in all directions, and the room is radiating in all directions, and some of that radiation is absorbed by the probe. And it turns out that the probe doesn't change temperature because the outgoing radiation from it is the same as the incoming that it's absorbing. So when the probe is moved over the ice, it's radiating just as much as it was before. It starts out at the same temperature, and the room is doing what it was before. It's radiating, and some of that radiation from the walls and ceilings comes in and strikes and is absorbed by the probe. But the ice is emitting far less radiation than the surfaces of the room, and the lower surface of the probe is exposed to the ice. So this lower surface of the probe is radiating like it was before, but it's receiving a much smaller amount of radiation from the ice. And because it's radiating more than it receives, it cools off. Now it's time to fill the cone with oxygen. So there it's filling up. Okay, I have recorded all of the initial temperatures. Now it is time to place the cone on the ice. After I do that, I immediately start the stopwatch. Okay, it's been 1 minute. The probe inside the top has dropped well over 5 degrees C. The wall of the cone at the bottom has dropped there it is, about 1 degree. Less than 1 degree. It started at 20.8. Okay, I hooked up the CO2. Let's turn it on. So I hear the gas filling the cone, and I'm going to do my little check here with the toothpick. Very high tech. So you can see when I hold the toothpick up to the hole that oxygen is being pushed out. The carbon dioxide is filling from the bottom up. It's pushing the oxygen out. If I light this toothpick with a flame and it actually puts the flame out, then I know it's full of CO2. So the cone is filled with carbon dioxide. So let's go ahead and set it on the ice and we'll see what happens. Start stopwatch. So here we have the cone sitting over the mixture of salt and ice, and it's filled almost entirely with oxygen. Let's try to understand what happened. Let's say for a moment that the glass probe was in this position about 2.5 feet above the ice without the cone. The bowl of ice actually takes up a very small portion of the total view that the probe has of its surroundings. And without the cone, it would have very little effect on the temperature of the probe. In fact, I've done this. I've put the probe at this distance above the ice without the cone, and its temperature didn't drop at all. So that changes when the cone is in place. Its surface emits very little infrared, absorbs very little, but it's a very good reflector. And so it serves as a shield from the infrared in the rest of the room. All the infrared that's zooming around does not affect what's happening inside the cone. If any surface in the cone, and that's any surface, remember all of them are always emitting, some more than others, but they're always emitting. So if any surface emits a photon of infrared, maybe it's this spot right here, and it emits in this direction. It will strike the opposite surface of the cone, be reflected. It'll hit here, be reflected again, and reflected again, and it'll end up striking the surface of the ice where it's absorbed. Ice is an extremely good absorber of infrared. So the ice is a very good absorber of infrared. Any infrared ray from any direction that comes is almost certainly going to be absorbed by it. But because it's very cold, it emits far less than it absorbs. So the combination of the cone with the presence of the very cold ice at the bottom has the effect of dramatically reducing the intensity of the infrared radiation inside the cone. Now, the glass probe is emitting just as much infrared as it was before, but it's receiving less because of the effect of the ice and the cone. And so because it's receiving less than it's emitting, the net effect is that it loses heat and cools off. The oxygen is in the cone in order to displace air. Air has a bit of water vapor in it, which emits infrared. With oxygen inside the cone, the infrared intensity is less than it would be with air. In fact, even though air is about only 1% water vapor, that little bit radiates almost as much as if the cone were full of CO2. So the net effect of all of this is that the probe is cooled by radiating, and over a 5-minute period, its temperature dropped 5.4 degrees. So now we have the situation where the cone is filled with carbon dioxide instead. And with the presence of the salt at the bottom, we have a situation where the amount of infrared that hits the glass probe is a lot less than what is leaving it. And it cools by radiation. What's different here is that carbon dioxide, unlike oxygen, can emit infrared. And so at any given moment, a molecule of carbon dioxide might emit a photon of infrared. It might go this direction and end up striking the glass probe, which would absorb it. And so the effect of the carbon dioxide is to add a little bit to the overall intensity of the infrared radiation inside the cone. This means that the net loss of heat by the probe is less, and therefore its temperature drop would be less over the same period of time. And that's what we found. With the oxygen, the glass probe dropped 5.4 degrees in 5 minutes. Over the same period of time, with carbon dioxide in there instead, the temperature dropped 4.8 degrees. So in the experiment, we saw that carbon dioxide radiates infrared. And it's important to know that if you want to understand its role in the atmosphere when it comes to the Earth giving off heat to outer space. So it also turns out that my demonstration apparatus is kind of like an upside down version of the Earth and outer space and the atmosphere in between. So instead of the Earth, we had a glass probe, which has a very high emissivity, just like the Earth's surface and the surface of the oceans and any other water. They have very high emissivity. And then there's the ice, which is very cold, like outer space. And then there were the gases in between contained by the cone, first oxygen and then carbon dioxide. So we saw that when oxygen was in the cone, it cooled off at a certain rate. That is, the probe cooled off at a certain rate as it was radiating. And then later, when there was carbon dioxide in the cone instead, it cooled off more slowly. And so it is with the Earth at night. If there was only nitrogen and oxygen in the atmosphere and no CO2, at night the Earth would cool off much more quickly. And in general, it would be much colder too. But because there's carbon dioxide in the atmosphere and also water vapor, it's much different. And there's life on Earth. So the atmosphere has various layers. The one that we are most familiar with is the troposphere, which is the lower atmosphere. It contains the majority of the mass of the atmosphere and practically all of the water. So well over 99% is in the troposphere, which goes up to roughly 10 kilometers or so. So there are clouds and rain and snow, maybe ice crystals and whatever, but most of the water vapor in the troposphere, most of the water is in the form of vapor, which is a gas. It's invisible. And it's very roughly 1%. There's a wide variation in this. In the tropics, where it's warm, it could be 2 or 3%. In the poles, where it's very cold, it's a small fraction of 1%. But worldwide, that's a very rough average. And this is 10,000 parts per million water vapor. There's also carbon dioxide in the troposphere, and it is a much smaller portion of the atmosphere. It's 410 parts per million. And not only is there more water vapor in the troposphere, but it absorbs even more infrared than carbon dioxide does. So in the lower atmosphere, the primary greenhouse gas is water vapor. Carbon dioxide plays an important role. It absorbs a substantial fraction, but water vapor absorbs most of the outgoing infrared radiation. And so what happens is, if a photon of infrared emerges from the Earth's surface, a fraction of it, well less than half, will go straight to outer space and not be absorbed. But most of the infrared that's emitted by any spot on the Earth's surface in various directions is absorbed in 10 or 20 meters, maybe a couple hundred meters, but the large majority of it is absorbed before it goes very far. Now I'm going to use the word photon, which you may not know exactly what it means. It's like this tiny little bit of electromagnetic energy. All electromagnetic energy, which is visible light, X-rays, microwaves, infrared, it all comes as a stream of little tiny bursts of energy called photons. And it's just a little easier to talk about this using the word photon. So here we go. So the Earth surface and the oceans and whatever emit this infrared, and most of it's absorbed before it goes very far in the lower atmosphere. And any gas that absorbs infrared, and these are namely water vapor and carbon dioxide, they will also emit. So a molecule of water vapor might emit a photon, and it goes a little ways and it's absorbed, it stops, and it's absorbed by another molecule. A molecule of carbon dioxide might emit a photon, and it goes this way, and it's absorbed before it goes very far. Now, the higher you get in the atmosphere, the less dense it is. So the molecules are farther apart, and on average, the photons will travel farther. So if a photon is emitted here, and it's going to go farther than near the Earth's surface. And so the higher you go, on average, the farther that photon is going to travel. The troposphere, like I said, contains a vast majority of the water vapor in the atmosphere. In the stratosphere, as a rough average, the water vapor is 5 to 7 parts per million. And the carbon dioxide is still 410 parts per million. Now these are concentrations, so there's not the same amount of carbon dioxide in the stratosphere as there is in the troposphere, but there's the same concentration, the same fraction as there is here. So it's a very different situation in the upper atmosphere. And carbon dioxide is the primary greenhouse gas in the stratosphere. So you keep going higher and higher in the atmosphere, and there's a region at a certain altitude where if a carbon dioxide molecule emits a photon of infrared, it has a 50% chance of just keeping going and going into outer space, not being absorbed by another molecule, and it's gone forever. It's not coming back. So again, this emission can happen in any direction, but if it happens to go to outer space and it's not absorbed, then it's left. So this is the region where that starts to happen, where the photons make it to outer space. The altitude where this happens depends on the concentration of carbon dioxide. A century or so ago, the level of carbon dioxide was approximately 280 parts per million. And so this region was lower down. The amount of carbon dioxide in the atmosphere is going up every year, every decade. And so this sort of boundary where this emission to outer space starts to happen goes higher and higher. And if the concentration of carbon dioxide were to double from what it was historically, then the altitude at which it emits to outer space, roughly speaking, would double. And so the reason that's important is that the difference between this altitude and that altitude is this whole part of the atmosphere here where there's still this radiation and absorption going on. A molecule radiates, it's absorbed by another. A molecule radiates, it's absorbed by another, and so on. This radiation and re-radiation happens in the part of the atmosphere where the density of the gases is high enough. So if this layer of the atmosphere that goes up to the boundary where it starts to be emitted to outer space, if that becomes thicker, it's like adding an extra layer of insulation to the atmosphere. Just as if you added insulation to the wall of a house, it made it thicker, the heat has farther to go through the wall to be conducted to the outside, and so it would keep the house warmer for a given amount of heat input. Now the mechanism is different. Here it's radiation heat transfer, whereas in the wall of a house it is convection. But the point is that if there's a farther distance to go, it has a greater blocking effect for the transfer of the heat. It is true that in the lower atmosphere, increasing the concentration of carbon dioxide has very little effect on how much outgoing radiation is blocked. And so this is called saturation. It's kind of like if you draw a thick curtain in a room, it basically darkens the room, it blocks practically all the light. If you draw a second curtain over it, that isn't going to make the room significantly darker because it was blocked already. So likewise, the presence of CO2 in the lower atmosphere, it blocks outgoing radiation by absorbing it, and then it's re-emitted and so on. And then increasing the concentration in the lower atmosphere will not increase the amount that is blocked before it goes to outer space. About the same amount will go straight to outer space, and about the same amount will be blocked, only a slightly larger amount. And so this is referred to as saturation. And because the lower atmosphere in regards to infrared radiation is saturated, increasing the concentration will not really affect much what happens in this process in the lower atmosphere. It's what happens in the upper atmosphere that matters. And so that is why I focused on carbon dioxide emitting radiation, and that's why I set up the demonstration the way I did. It's just to focus your attention on that. And also I did it because I like doing hands-on science. I had fun putting it together. So thank you for watching, and have a great day.